Hello students, welcome to EPG Pathshala and I am Rima Gupta from University of Delhi. So today we are going to discuss about the module Excitons and excitonic Bohr radius energy levels splitting from paper Nanoscience and Nanotechnology 1. After studying this module, you should be able to understand semiconductors and exciton, quantum confinement, quantum dots and nanoparticles. You will be able to understand by the band gap energy for a quantum dot and its confinement energy. We will be discussing about bound exciton energy, electronic properties and quantum dot production. So before moving further, let's discuss about semiconductors and excitons. So the atomic and molecular systems, the energy transfer can occur within a molecule through intermolecular vibrational energy redistributions and electronic state coupling. So the energy transfer between molecules can occur through coupling of rotations, vibrations or electronic excitations. In all of these energy transfer mechanism, the probability for the coupling depends on the relative energies of the states being coupled. So within a molecule, the energy between the first excited state and the ground state depends on the build-up of atomic orbitals to form the molecular bands, that is the highest occupied molecular orbital, which we call as HOMO, being the ground state, and the lowest unoccupied molecular orbital, that is LUMO, being the first excited state. In solid state systems, the magnitude of energy difference between HOMO and LUMO referred to the band gap, that is EG, which can be separated into one of the following three types in metals, semiconductors and insulators. So in a metal, the energy of HOMO and LUMO orbital overlap and the electron promotion occurs with very little or no impetus. In insulators, energy gap, that is EG, is very large and electronic excitation is a weak or unlikely process. Whereas, on the other hand, the semiconductors, as their name suggests, have a measurable band gap and not so significant as to limit electronic excitations. The states that lie at or below the HOMO are in the valence band, and the states that lie at or above the LUMO are in the conduction band, that is CB. In large-scale semiconductor materials, the build-up of the atomic orbitals in forming the molecular orbitals, including many atoms, each with slightly different energies. So the electronic excitation can occur in a semiconductor when a photon with energy equal to or greater than the band gap, that is EG, is absorbed. So the promoted electron leaves behind the vacancy and the electron deficient energy behaves as a positive charge particle and is referred to as a hole. So the electron energy and distribution of the photo-generated electrons and holes are described quantum mechanically by their wave functions, by their probability distributions and by their permitted regions. The breadth of the probability distribution of the electrons and holes determine their effective size and are referred to as the electron, which we call it as AE, and hole, that is AH, Bohr radii. As for all the charged particles, there are Coulombic interactions between the electrons and holes, and the strength of these interactions determine if the electrons and holes can be treated separately or as coulombically bond electron-hole pairs termed as exciton. So there is preferred separation distance between the electron and the hole probability distribution in an exciton, and this distance is determined by the exciton Bohr radius, that is AB.
Quantum confinement. Decreasing the size of a semiconductor particle in one, two, or all three physical dimensions can change the electronic structure of the material by confining the spatial distribution of the exciton, electron, or even whole wave functions. Since there is a continuum of states for each of the dimensions that do not exhibit quantum confinement, therefore the density of states depend on the dimensionality of the material, which is shown in this figure. The states of quantum dots become discrete with energies of a few hundred MeVs between the quantized states. So students, you can see in the figure D that there is a similar shift of the band gap to higher energy than the bulk Eg. In a two-dimensional system, that is in figure C, the states resemble a saw-like quasi-quantum. The energy between these states can be a few hundred MeV, and the band gap can also shift a few hundred MeV above Eg. So students, you can see the figure on the right hand side showing the density of states in energy for a semiconductor as the degree of quantum confinement increases. On the left in figure A, it shows the continuous nature of the bulk material. Figure B depicts confinement in one-dimensional. Figure C shows in two-dimensional, and figure D shows the density of states become discrete for confinement in all three dimensions. The strong, medium, and weak confinement terms mentioned are a result of the specific size in each dimension relative to Ag, Ae, and Ah. In the case of strongly confined systems, the restricted dimensions are smaller than both Ae and Ah in an intermediate confinement regime. The size of the confined dimension is smaller than that of Ae but greater than Ah. In a weak confined system, the restricted dimensions are larger than both Ae and Ah but small enough that the wave function of the exciton is perturbed and an energetic shift of this state to higher energy results. The extent of confinement also affects the spatial overlap of the electron and hole wave functions and the Coulombic interactions between them. Bound electron-hole pairs or exciton should also be treated as quantum mechanical system with wave functions that resemble this simple hydrogen atom system. The photo-generated electron-hole interactions are weak in bulk semiconductors and the binding energies are sufficiently small that the electron-hole pairs are not bound at room temperature. Instead, they dissociate into separate electron and holes. The dependence of the oscillator strength and the binding energy depends on how many degrees of confinements are there. The energy interactions due to energy or we can say the energy interactions due to quantum confinement are often large compared to the Coulomb interaction terms. Furthermore, the dimensionality may not permit the electrons and holes to be stabilized at a preferred length within the Coulombic potential, and excitons may not be formed. Such is the case for small quantum dots, where the electrons and holes are forced to occupy the same volume, and the electrons and holes weakly interact and can be considered as independent systems. Quantum dots are novel polycrystalline, or we can say quantum dots are novel nanocrystalline semiconductor materials whose electrical as well as optical properties strongly depend upon the size and shape of the dots. The diameter of quantum dot can vary from 2 to 10 nanometer or on the order of 10 to 50 atomic lengths. Due to their small size, quantum dots have very large surface to volume ratio. As a result, they have properties somewhere between the individual atoms or molecules and the bulk materials. Quantum dots can be produced either from a single element or more than one element. The materials with dimensions in the nanometer scales are called nanoparticles, and they are frequently investigated by the researchers to study the novel properties at this scale. The majority of quantum dots are prepared from semiconducting material like silicon, germanium, cadmium, selenide, cadmium sulfide, and so on. Since the size of quantum dot is of the order of nanometers, they are not single atoms, rather, they are comprising several atoms. Different colors. So we can say that quantum dots can produce different colors depending on its size. So this figure shows different light being emitted from nanoparticles having variable sizes. So the top figure shows the long wave ultraviolet illumination, whereas the bottom figure shows the ambient illumination. The solutions are in order of increasing particle size, that is longer growth time. As the quantum dots are irradiated with ultraviolet light, some of the electrons absorb adequate energy in order to break free from the atoms. Therefore, these electrons become free to move around the nanoparticle, thereby creating the conduction band wherein the electrons freely move through the material and conduct electricity. When the electrons return back to the original orbit around the atom or the valence band, the light is emitted whose color depends on the difference in conduction band energy and valence band energy, which you all can see in this figure. So in this figure, electrons in a quantum dot generates light. So the smaller the nanoparticle is, higher is the energy difference between the valence and conduction bands, resulting in the deeper blue color. And for a large nanoparticle, the energy difference between the valence band and the conduction band is lower, which shifts the glow towards red end. Almost all the semiconductor materials can be used to prepare the quantum dots. The nanoparticles of all the semiconductor materials behave as quantum dot. The gap between the valence and conduction band, which is present in all semiconductors, causes the quantum dots to fluorescence.
Theoretical understanding. We can say that semiconductor crystals of size less than or double the Bohr radius of the exciton experience quantum confinement. So the particle in a box model can be used to model the energy levels, giving energy states dependent on the size of potential well. So these separate scenarios which can occur are: the first is strong confinement. The radius of the quantum dot is less than the Bohr radius for both the electron and the hole. Second is the intermediate confinement. In this, the radius of quantum dot is less than the Bohr radius of one of the electron or hole, but not the other. The third is weak confinement. So in this, the radius of quantum dot is greater than the Bohr radius of both the electrons and holes. So the sum of all the energies involved with the quantum dots is expressed as the total energy E, which is the sum of band gap energy, confinement energy, and exciton energy. So this energy is comprised of three terms. We call it as band gap energy, confinement energy, and bound exciton energy.
So the first is band gap energy. The band theory in solids tell us about the allowed and disallowed energy states. Here allowed are the energy bands and disallowed are the forbidden bands or the band gaps. The numerous models have been developed to model the band structure of the solids, such as Kronig-Penney model or density functional theory, and so on. In strong confinement region, the band gap increases when the quantum dot is smaller than the exciton Bohr radius owing to the splitting of energy bands. The total emitted energy increases and the emission occurs at the various wavelengths, resulting in white light. So the exciton Bohr radius can be expressed as AB star, which is equal to epsilon r times m by mu into AB. Here, epsilon is the dielectric constant or relative permittivity, m is the mass, mu is the reduced mass, A, B represents the Bohr radius, and AB star is the exciton Bohr radius. Now the next term is confinement energy. A particle in a box model can be used to model an exciton. The variations in particle size allow to control the confinement energy, and solution of particle in a box model represents the exciton energy, which is as follows. So it is represented as E confinement is equal to h cut square pi square upon 2a square times 1 upon me plus 1 upon mh, which in turn equal to h cut square pi square upon 2 mu a square, where me is the mass of electron, mh is the mass of hole, and mu is the reduced mass. Now the next term is bound exciton energy. The Coulombic attractions occur between the electrons having negative charge and holes having positive charge. The energy of these attractions is directly proportional to Rydberg energy and varies inversely with the square of the dielectric constant. The term assumes significance as the semiconductor crystal becomes smaller than the Bohr radius of exciton and is given by E exciton is equal to minus 1 upon epsilon r square times mu by me times ry, which is equal to minus ry star, where ry is the Rydberg constants. Now substituting the values of these energies in the expression of the total energy which we have discussed earlier, we can find the total energy. A quantum dot is confined in all three spatial dimensions, but semiconductors with other modes of confinement includes quantum wires, which includes holes or electrons confined in two spatial dimensions with 1 degree of freedom, and quantum wells, which are the confinement in one spatial dimension with 2 degree of freedom. So taking into account each of these three terms, then the total energy can be simplified further as E is equal to E band gap plus E confinement plus E exciton. Therefore, we get that expression for total energy is E band gap plus h cut square pi square upon 2 mu a square minus ry star. Now comes electronic and optical properties. So let's discuss first the optical properties. The wavelength of the emitted light in a quantum dot depends upon its size. We have discussed this earlier. With decreasing the size of the dot, the wavelength of the emission shortens and demonstrate a blue shift in electromagnetic spectrum of the visible light. Similarly, when the size of quantum dot is increased, the wavelength experiences a red shift. Using de Broglie's relation, energy is E is equal to hc by lambda. So this shows that a particular wavelength of the emitted light can be determined. This makes quantum dots very useful to finely tune specific properties like the wavelength of the emitted light. So when the quantum dots are illuminated by UV light, some of the electrons receive enough energy to break free from the atoms, and this capability allows them to move around the nanoparticles, creating a conduction band in which the electrons are free to move through a material and conduct electricity. When these electrons drop back into outer orbit around the atom, that is the valence band, they emit light. The color of the light depends on the energy difference between the conduction band and the valence band. Now, the second type of properties are electronic properties. Small sized crystals have large electronic band gaps, implying the occurrence of a larger energy difference between the energy states. In these cases, the larger energy is required to promote the electron to the excited state, and also more energy is emitted when electrons return to their original energy levels. When a semiconductor is incident with a light photon having more energy than its band gap, then an electron is excited from the valence band to the conduction band, which is shown in this figure. The excitation of electron to a higher energy state results in the creation of a hole in the valence band. A hole can be simple, described as the absence of electron, and it has opposite charge to the electron. That is, it is positively charged. The electron and hole experience Coulomb attraction and form an exciton. So the exciton itself is an electrically neutral quasi-particle, and it can be found in semiconductors, insulators, and also in some liquids. Yakov Frenkel first introduced the concept of exciton in 1931 during the discussion and discuss about the excitations of atoms in an insulator lattice. Now comes quantum dot productions. Quantum dots linked together can form the basic building blocks of a variety of crystalline and non-crystalline nanostructures. The quantum dots can be linked together as molecules to form more complex structures like lattices, polymer backbones, and can be incorporated into thin polymer films, which are represented in the figures shown in the right hand side. So these figures shows the quantum dots utilized in a variety of structures including molecular, crystalline, polymeric, and even in thin films. So the quantum dot can be prepared by a variety of different techniques such as colloidal synthesis, electrochemical assembly, fabrication, and viral assembly.
So students, let us summarize what we have learned in this module. So there is a continuum of states for each of the dimensions that do not exhibit quantum confinement. Therefore, the density of states depend on the dimensionality of the material. The states of quantum dot become discrete with the energies of a few hundred MeVs between the quantized states. So the materials with their dimensions in nanometer scale are called nanoparticles, and they are frequently investigated by the researchers to study the novel properties at this scale. The majority of quantum dots are prepared from semiconducting materials like silicon, germanium, cadmium selenide, cadmium sulfide, and so on. The smaller the nanoparticle is, higher is the energy difference between the valence and conduction band. So students, we have discussed in this module that it results in deeper blue color. For a larger nanoparticles, the energy difference between the energy band and the conduction band is lower, which shifts to glow towards red. The total energy involved with the quantum dots comprises three energies which we have discussed: band gap energy, confinement energy, and exciton energy. So the quantum dots linked together can form the basic building blocks of a variety of crystalline and non-crystalline nanostructures. The quantum dots can be linked together as the molecules to form complex structures. Example, lattices, polymeric backbones, and can also be incorporated into thin polymer films. Thank you.